This is 9.5 alternating series. Okay, so thus far a lot of our series that we've been talking about needed to have positive terms. And what do you do if the terms don't always come out to be positive numbers? One of the most prevalent series that we'll see where there are negative terms is the alternating series. That's where the terms alternate between positive and negative values. As we said when we were talking about sequences, when we have something like 1, negative 1/2, positive 1/4, negative 1/8, etc. When we go to write the nth term for this, you recall that what we did was we said we would multiply the formula that's producing the numerical part of the term by -1 raised to a power. And that power is generally either n or n plus 1, or perhaps even n minus 1, so that you start with the right sign. So for n equals 1, we of course want the answer to be positive. And if we put 1 into the term I've put, -1 to the nth, it'll be negative. So we are going to have either +1 or -1. If we're starting with 1, that is. Okay? And this is a series that starts with 1 and multiplies by 1/2 each time. So the numerator is always 1. The denominator is a power of 2. The first one is 2 to the 0, which is 1. So this is going to have to be n minus 1 as the power. And that's why sometimes if the expression itself involves the subtraction of 1, then a lot of times instead of using n plus 1, we'll use n minus 1 so that they match a little bit better. It's not absolutely required, but it lends a little bit of nice symmetry to the problem. So that would be one way to write the terms of this series, of this sequence, excuse me. Now, another thought would be, okay, since we are starting with a number and multiplying by -1/2 each time to go from term to term, we can think of that as a geometric series, multiplication by -1/2. So the first term is 1 times r, which is -1/2, to the nth. And remember, with geometric series, we generally start with 0. And so if we made this our series with n starting at 0, let's see if it actually produces the right numbers. -1/2 to the 0 is 1. Yes. Plus -1/2 to the first, multiplied by 1. I didn't say that the first time, but of course that's not going to change anything. So -1/2 to the first is -1/2. Plus -1/2 squared is +1/4. -1/2 cubed is -1/8, etc. And of course that is producing the correct numbers. And so changing the addition of negatives to subtraction makes the series this one. Now that doesn't negate the fact that what we wrote above is actually true. I recall saying earlier that the way that you write the term of the sequence is not unique. And a lot of times we can make it a different formulation by starting in it a number other than 1. Like here, starting at 0, which we generally will do with geometric sequences, is pretty common. And in fact, we'll probably always, if it's geometric, and of course 1 times anything, I'm just rewriting that expression so that it's simplified. So this is the geometric series in sigma notation that we just talked about. That can then be thought of algebraically if we want to. This is not a requirement, just at this stage, it's just a thing we can do. Remember that when you have a product, like a times b, that's being exponentiated, you distribute that exponent to each factor. And so that means that this could become -1 to the nth times +1/2 to the nth. That's a lot like the one we wrote up there in blue, but starting at 0 for the first n instead of starting with 1. So both of those are correct. The last one, the one written in pink, is the more standard version of that, the one that you should strive for. So now I ask you, does that converge? Well, since it's geometric, we can use the geometric test, geometric series test. Remember, with geometric, we identify the first term, and we find r, and we already identify that r is -1/2. And then we think about what would the absolute value of that be, and we think, well, is that either between 0 and 1, or is that bigger than 1 when we take its absolute value? And since the absolute value of this r falls between 0 and 1, that means that this series equals 1 to infinity, written in either this way or this way, doesn't really matter. Since we're treating it geometrically, kind of seeing that a, which is the invisible 1, times r to the nth is expected. So that's probably the best form, since we're treating it geometrically. And of course our conclusion is convergence. All right. So if you look at Theorem 9.14, you can kind of see an indication of whether you want the first term to be positive or negative and then have the rest alternate. Depends on whether you pick the power on -1 to be n or n plus 1. And this is a more generic series. It's not necessarily geometric. So you notice that for most of the time we're still going to start with n equals 1, except for when it's geometric. Okay, so those are the two variations of alternating series. There'll be a power of -1 multiplied by an expression called a sub n. And this is called the alternating series test. So this is the next in our list of tests for the convergence of series. Of course, it does have to be alternating to even contemplate using this test. Otherwise, it would make absolutely no sense. So that's its name, alternating series test. And here, if both conditions are met, number 1 is that the limit as n approaches infinity of a sub n. And I want you to realize, look up at the declaration of what a sub n is. the a sub n is the thing that the power of -1 is multiplied by. It does not include the power of -1. So it's just the rest of it, not the power of -1. So if the limit of a sub n as n goes to infinity is 0, and the second condition is that any next term, if you know what the current term is a sub n, the next term always has to be less than or equal to the current term for all n. Okay, that's the alternating series test. It's a pretty simple test, and when we can use it, it's a really handy one, and it goes pretty fast, and it's accessible. So let's move on to some examples. First example, the series from n equals 1 to infinity, produced by the formula -1 raised to the n plus 1 multiplied by 1 over n. All right. So you might, to at least start, expand the series at least sometimes so that you get a sense that it is alternating from the answers you're getting. So if I put in 1, 1 plus 1 is 2, -1 squared is +1, times 1 over 1 is 1 over 1, which is 1, of course. Then putting in 2 for n, 2 plus 1 is 3, -1 cubed is -1, so this will be a negative answer, 1 over 2. One to the fourth is positive, so yes, this is alternating between positive and negative answers. You want to guess what the name of this series is? It's actually a nameable one that you should recognize, related to something we've already talked about. This is called the alternating harmonic series. And just like the harmonic series, it's a named one, and then once we figure out whether it converges or diverges, you'll be able to just make that claim without having to prove it every time. We're going to prove it this once, and then you can use that information as needed for any problem that you have. Okay, so test 1. What I'm going to ask that you do to make sure that it's very clear that you're understanding, I want you to first, when it's alternating, tell me that it's alternating. So I'm pretending like I didn't write that over to the side. Tell me that it's alternating once you've determined that, and that means we're entering the alternating series test. And that's the mention of the name of the test that I've asked you to put in by writing the word alternating, like writing the word geometric. You've told me what you're thinking and what theorem you're using, so that's plenty. You will not have to say that it converges or whatever by the... Oh, and by the way, the alternating series test only finds convergence. So it will not find divergence by itself. So I should have read up here and written that if both of those conditions are met, the series converges. So anyway, this is alternating. The next thing I'm going to ask that you do is identify what a sub n is. I want to make sure you can separate the power of -1 away from what a sub n is. A sub n is the part that does not have that power of -1 attached to it, so it's 1 over n. So, test 1. And I'm doing exactly what I would like for you to do. Test 1. The limit as n approaches infinity, and then substitute in your a sub n statement, and then calculate that limit. 1 divided by an increasingly bigger and bigger value is headed towards 0. That checks out. And by putting that check mark, you're kind of telling me, yep, it passed that part of the test. We're good to go. What's next? Then I'd like for you to write down a sub n plus 1. Calculate what that would be by substituting n plus 1 into your a sub n formula. Then leave a little bit of space and write what a sub n is equal to. And then tell me that that's a sub n. And now I want to compare these. Now don't jump to the conclusion that it's going to be what we want it to be. You really have to think about it each time, because this is where it could go wrong and not be a conclusion of convergence. The first fraction has a larger denominator, which means that it's a smaller number. So the first fraction is always less than, technically just less than, but we're going to write or equals to because that or equal to is part of the theorem. So it isn't a false statement. It never is equal to, but it could be, I suppose. So we've now established that the second condition is met, and that means, of course, that the series that we're considering, the alternating harmonic series, converges. Okay, so that's a result that you can put in your hat, keep that whenever the alternating harmonic series comes up in conversation, you can just assume that everybody knows that it converges now and work from that standpoint. All right, so let's do another one. Let's see, n equals 1 to infinity, n over negative 3 to the n minus 1. So again, it's not a bad idea, at least at first, for you to do some substitutions and get a feel for what you're dealing with and if it really is alternating or not. So putting in 1, I'm going to get 1. And then 1 minus 1 is 0. Negative 3 to the 0 is 1. Then the next term I'm going to put in 2. 2 minus 1 is 1. Negative 3 to the first is negative 3, which I can write the 3 down here and the negative out in front. Then put in 3. Negative 3 to the 3 minus 1 is 2. Negative 3 squared is 9. That's positive, so I can put a plus here. And now you can tell that it's alternating. Notice that I'm not so super concerned with the simplification when I'm doing this for the thought process of, is this alternating or not? So you can say, yep, it alternates. That means we're using the alternates. So the next thing I want you to write down is what is a sub n? This is where it gets tricky, because this one is not written in a form where you can automatically just write what it is. So let's go back out here and work with that algebraically so we can figure out what would that be if we kind of separated the negative 1 part out of it. So using that property we talked about earlier, the product of negative 1 times 3, we can distribute that exponent to the negative 1 and to the positive 3. And that then is writable. That negative 1 in the numerator denominator doesn't matter. If it's positive 1, the whole thing's positive. If it's negative 1, the whole thing's negative. So I could write that negative 1 to the n minus 1 kind of in the numerator position, if you will. And it won't hurt anything. And it looks like what we're expecting now. Okay, so that's an expression of it that makes it look like it's in the form. Now we can identify a sub n very easily and clearly is n over 3 to the n minus 1. Okay, so that's an n. So let's enter the test. that limit, if I'm thinking about substituting n in, and a lot of times you want to think a little bit ahead, that'll become infinity over infinity. So what I'm going to need to do to find that limit is I'm going to have to change it into x, because I'm thinking of using L'Hopital's rule. So I'm going to change this to a function of x. So that's x over 3 to the x minus 1. And then we'll calculate the limit as x approaches infinity. X over 3 to the x, which of course is infinity over infinity. So we can use L'Hopital's rule. So this limit can be found by now taking the limit as x approaches infinity of the derivative of the numerator is 1. The derivative of the denominator is itself, 3 to the x, times the natural logarithm of the base of that power, so times natural log of 3. And that denominator is still going towards infinity. The numerator is now constant. Any constant divided by a tremendously large number is headed toward 0. And that means that since the limit for x gave us that answer, the limit as n approaches infinity of n over 3 to the n minus 1 is 0, which is what we needed to show. And we're good to go now to number 2. Okay, now for this next part, I'm going to do something that's going to feel like magic, because it sort of is in a way. It's mathematical magic, if you will. I want you to just take on faith. No, maybe you can just discover this with a little bit of thought. But do you agree that this is a true statement? 1/3 is less than or equal to n over n plus 1. At least for the n's that we're considering, positive integers greater than or equal to 1. Well, just do a few substitutions. The first substitution will give us 1/2 is 1/3 smaller than 1/2. Yes. Now put in 2. 2/3 is 1/3 smaller than 2/3. Yes. Put in 3. 3/4. Still less than? Yes. 4/5. 5/6. 6/7. 100 over 101. Yes, those are all bigger than 1/3. So that's a true statement. You may be wondering, well, where did that come from? Well, that's the magic of this. And I'll show you in a minute what I did. It isn't as magical as I'm pretending. So what I want to do on the left side of this inequality is multiply the left side by a form of 1. 3 to the n minus 1 over itself. Now, multiplying the left side by 1 will not change the inequality. It won't even change the value of the left side. It'll just change what it looks like. Okay? So, doing that multiplication, 1 times 3 to the n minus 1, of course, is itself 3 to the n minus 1. 3 to the first times 3 to the n minus 1. Add the exponents. 1 plus n minus 1 is going to be n. Okay, so I'm just doing logical, reasonable things to this inequality that are algebraically fair to do. So now what I want to do with that is I want to multiply both sides by n plus 1 over 3 to the n minus 1. Now you can multiply both sides of an inequality by the same thing. If it's a positive thing you're multiplying by, it does not change the inequality. However, if you're multiplying by a negative thing, you have to change the direction of the inequality. n is 1 or bigger, so the numerator n plus 1 is definitely positive, and 3 to any power is a positive number. So we are definitely multiplying both sides by a positive number, so we do not change the inequality. So on the left side, the 3 to the n minus 1's cancel, leaving n plus 1 in the numerator, and 3 to the nth in the denominator. On the other side, the n plus 1's cancel, leaving n divided by 3 to the n minus 1. Now, if we think about what our a sub n was, go back and look at that a second, n over 3 to the n minus 1, right up there next to where I wrote alternates, n over 3 to the n minus 1, that's the right-hand side of our inequality. So by substitution, that's a sub n. And if I were to put n plus 1 in for each n on that expression, I would get n plus 1 in the numerator, and n plus 1 minus 1 would simplify to be 3 to the nth, and so that is the expression of a sub n plus 1. And that's a proof because we started with a true statement at the very top there that 1/3 only did algebraically correct and logical steps to the inequality until it became what I wanted to prove. And here's the magical part of that. And by the way, let me write the conclusion and I'll tell you how I did that little magical thing. So we've found both first and second conditions for the alternating series test were met. So that means, of course, that the series n equals 1 to infinity of n over negative 3 to the n minus 1. Oops, I wrote something that doesn't belong. Get rid of that. I forgot to write something that does belong. Excuse me. That's negative 3 to the n minus 1. There we go. Converges. And we could, at this point, be a little bit redundant and say it converges by the alternating series test if you wanted to. But because I wrote alternating up above, that's not really required. All right, so if you look at the expansion of this one and look at the answers in reduced form, the first one is 1, then 2/3, then 1/3. Do you believe that those fractions are such that the one in front is always greater than or equal to the next one behind it? 1 is bigger than 2/3. 2/3 is bigger than 1/3, and we could keep going. So you could have a sense that you think that's true. It's not a proof. It's an intuition, and it's a good one, and it'll lead you to the right place. But if you think that's true, you're going to want to be able to prove that it's true. And so this is the magic I was talking about earlier. Just write down what you want to be true. Okay? I'm going to let you do some wishful thinking here. So that's what you want it to be. So what you could do then is take your a sub n statement. We've already seen that a couple times, but let me get it so you can see it. Take your n plus 1 your a sub n statement and substitute n plus 1 in for each n. So that'll become n plus 1. 3 to the n plus 1 minus 1 ends up simplifying to be 3 to the nth. And then a sub n, of course, is n over 3 to the n minus 1. So that's what we want to have happen. And what we have to do is play with this algebraically in a reasonable, logical, and correct way until it becomes an inequality that we know is always true for n greater than or equal to 1. So let's see. We could, if we wanted to, multiply both sides of this by 3 to the n minus 1 over n plus 1. Oops. Okay, and the n plus 1s will cancel, leaving 3 to the n minus 1 divided by 3 to the nth. Oh, and by the way, we can do that without changing the direction because 3 to the n minus 1 and n plus 1 are both always positive. And here on the right side, the 3 to the n minus 1s cancel, leaving n over n plus 1. On the left side, to divide fractions, to divide powers that have the same base, you keep the base and subtract the exponents. N minus 1 minus n is negative 1. And then writing that left side without a negative exponent is this. Is that statement right there always true? Equal to n over n plus 1 for n greater than or equal to 1. Yes. It's what we started with, the magical statement I started with last time. So I've now come to the point where I found something that is inherently true. It's 1 or bigger. So you might notice that all this is a reversal of the proof I have over there to the left side of this little box. This is actually quite prevalent in mathematical thinking, that you know what you want to prove, so sometimes you start at the end and sort of work backwards. And that's exactly what this is. So if we reverse the thoughts of this boxed statement, we'll end up with the statement over to the left, which is our proof for the second test. Part of the test is that to prove that. And by reversing these steps, we get that proof. So that's how a lot of times you're going to need to do that. Okay. So next one. N equals 1 to infinity, negative 1 to the n plus 1 times n plus 1 over n. So you see in this one the use of n plus 1 instead of n minus 1. Mostly that's chosen because there's already an n plus 1 in the rest of it. So it could have written that as negative 1 to the n minus 1 and it wouldn't change anything about the values that we're getting. Okay, so let's do a little substitution. We're starting with n equals 1. 1 plus 1 is 2, negative 1 squared is positive, and then substitute in 1 plus 1 over 1, you get 2. Putting in 2 for n, 2 plus 1 is 3, negative 1 cubed is negative 1, so that's going to be negative. Then putting in 2, that's going to be 2/3. What am I saying? 3 halves. Yikes. 3 halves. Then the next one will be positive 4/3. You can verify these. Minus 5/4 plus ... So we can see that this is alternating. It alternates. So we're going to see what we can do with the alternating series test. This time our a sub n is really easy to spot because that power of negative 1 is already separated out in front. So a sub n is the part that doesn't include that power of negative 1. Okay, so first part of the test, number 1. What is the limit as n approaches infinity of n plus 1 over n. This is that simple type I asked you to make sure that you could do. We could multiply this by 1 over n times over 1 over n and figure out that it's 1. But this is one I'd like for you to just be able to glance at and know. And I'm going to let you do that with linear over linear. Like this, it'll be the leading coefficient in the numerator divided by the leading coefficient in the denominator. In fact, any rational expression where the highest powers of n are the same number, you can do that same thing. And so for this process, I'm going to let you just jump to that conclusion. Now, is that what we want it to be? Well, no, it's not 0. So the alternating series test here does not prove anything by itself, because all it can prove is convergence. But a good thing has come out of this. Because that's not 0, what can I use now to draw a conclusion about this series? We actually can now. Have you figured out what it is? Do you remember? It's a hint. I'll tell you, it's the very first thing I said you should always try to do with any series. Not still coming to you? Okay, I'll help you. We know now that this one diverges. Why? Because the nth term is not headed towards 0. Remember that theorem we had if the nth term test that said that if the nth term is headed to something other than 0, the series definitely diverges. This nth term test for divergence. That's the short name of it. So if you are doing an alternating series test and test 1 fails, you actually have not wasted a bunch of time, because you just have to say, well, that's not 0, and therefore it diverges by the nth term test, which is actually kind of a cool result. Okay, now one of the interesting things about an alternating series that converges is that although we can't find the sum, remember we said that there are very few series for which we can find a sum. The geometric series that converges and the telescoping series that converges are the only ones for which we've really found formulas for S, what it converges to. And you'll notice if you look back at the alternating series tests, it did not say, oh, and if it converges, it will converge to capital S equals formula. It did not say that. So we can't jump to any conclusions. But if we were to start a series, let's just do one that we know converges. Let's do, 5 plus 5/4 plus 5/16 plus 5/64, etc. Oh, I'm sorry, I meant to make half of those. I need to make this alternating. My bad. I apologize. Let me go back and fix that. I got so wrapped up in thinking about what I'm multiplying by, I forgot to make it negative. So, sorry about that. So let's make this minus, plus, etc. So it's alternating. And we know that this alternating series converges metric and R is negative 1/4. And the absolute value of that's between 0 and 1. So we know it converges. So let's just take that as sort of as a given. I haven't written out a proof that it converges. I'm just indicating to you that we could, and very quickly know that this one converges. Okay, So the sum is, if you add up all the terms of that series, infinitely many things. If we were to find three, the idea is that the next thing that we add or subtract is getting closer and closer to 0 here. So kind of keep that in mind. So if we try to estimate what S is, so let me write that at the beginning. What is S approximately? I'm going to approximate it with a third partial sum. Add up the, because after that, what we're adding or subtracting is definitely getting closer, closer, and closer to 0. In fact, we already know what the next thing is 5/64ths. The next thing that's subtracted. This is 65/16ths, which of course is not the sum. It's just an approximation of the actual sum. And I'm using something for which we can find the sum so that we can check ourselves, but then we're going to apply this to any alternating series that's not necessarily geometric, because if it's alternating in geometric, we want to treat it as a geometric one and find its sum using the formula. But because we are using this one, we can check ourselves and see how we're doing. But we're going to pretend like for a second that this is one that we do not know how to find the sum for, even though we do. Now, what we've done when we've taken just the first three terms is we've taken the entire series and added the first three, and then what's left is the rest of those numbers, minus 5/64ths, plus 5/256, etc., etc., etc. And what we're going to call that is the remainder of the series. The remainder after three things have been pulled off, is going to be denoted by capital R sub 3 for the remainder of the series, is what the R stands for. And the 3 means after pulling off the first three, this is what's left. So I guess I could write over here, R sub 3 is negative 5/64ths plus 5 over, that is 256, right? I believe so. I say things like that and then I question myself, no, it's right, etc. That's the remainder part. Okay, so in a more general way, S is S sub n, when you take the first n items of the series, that partial sum, and chop that part off as an estimate of the entire series, what we're missing it by is, so S sub n is not S, but it's pretty close because that R sub n is supposed to be relatively small. And we can take that equation if we want to, and we can solve it for R sub n. I'm switching S sub n from both sides. That would be the remainder of the series. Okay. And what we want to do is we want the remainder of the series, partial sum, that's the error amount. This amount is the error in using S sub 3 to estimate S. That's how much we're off from actually having S, is the remaining part of the series, R sub n. So that's the error amount. And we're going to want to consider that error amount, we want that to be a positive number. Error is how far you are away from something. That's a distance. And s minus s sub n might not be necessarily, when you're subtracting, you don't necessarily know that it's positive. So to make it be positive, I'm going to put, so that tells me the distance I am away from the actual answer. And if I take the absolute value on the one side, I'll take the absolute value on the other side as well. Okay? And the theorem that I'm looking at, Theorem 9.15, says that if we have a convergent alternating series, then of course a sub n plus 1 is less than or equal to a sub n. What has to be true here is that this absolute value of the remaining part of the series has to be less than or equal to the first neglected term, a sub n plus 1. And I did make a mistake in something I wrote. In this theorem, they use a capital N. So I'm trying to be consistent with what you see in the book. Okay, so this is a really important result, because if you look at the example that I was working with, what I'm claiming is that since we know the sum, let's go ahead and find that sum of this alternating, this geometric, it is alternating, but this geometric series. Since it's geometric, we know that S is A, which is 5, the first term, divided by 1 minus R, and so 1 plus 1/4 is 5/4. I believe that turns out to be 4. Yep, that's 4. So that's the actual sum. And my claim is that, based on this one example that I've drawn, is that the actual sum is 4. If I were to take away s sub 3, which is we got was 65/16, that's the distance between the actual sum and our approximation. We subtract to get the difference between them and take the absolute value to make that positive. And the answer we're going to get for that is that's the remaining part of the series that we aren't using to estimate it. And if we (4 minus 65/16) is negative 1/16. The absolute value of negative 1/16 is 1/16. And I claim that that's less than or equal to the first term I neglected to use. So that's going to be a sub, since this was s sub 3. And this is r sub 3 as a consequence. Then a sub n plus 1 is a sub 3 plus 1, or a sub 4. So that means that 1/16 should be less than or equal to a sub 4. Okay? And is that true? Well, a sub 4 is 5/64. A sub 4 is, remember, the a sub n part does not include the negative part of it, because it's negative 1 to a power times a sub n. So the fourth term, if we neglect the negative, that's 5/64. 1/16 is 4/64. Is it true that that answer is less than or equal to 5/64? Yes, that'll always be true. So this is a really cool result in trying to estimate the error for when we don't know what the sum actually is. What we can do is we can kind of find out a little bit about how far we are away from, and we know that we're at least as close as the first neglected term. That the first neglected term being 5/64, whatever our error is, it's going to be less than that. As it turns out, in this case, we actually know it's 4/64. So definitely that's a true statement. All right, so that's kind of a neat result. And so you might want to put that into your memory, is that if I ask you to estimate what kind of error you're getting for an alternating series that converges, that this alternating series remainder theorem 9.15 is important to know. And it's always going to be that your error is less than or equal to the first neglected term, the first term you didn't use in your estimation. All right, so let's look at this question. N equals 1 to infinity of -1 to the n plus 1 times 1 over n factorial. Of course, this one does not produce a series, so because if it were geometric, it would be -1 to the n plus 1 times r to the something. So, and r is a number, and 1 over n factorial is not a constant. So that's not going to be geometric. Okay, so let's expand this out. When I put 1 in, 1 plus 1 is 2, -1 squared is +1, so that's going to end up being 1 over 1 factorial. When I put in 2, 2 plus 1 is 3, -1 cubed is -1, so that'll become -1 over 2 factorial. And after a while, you're going to get better at this too. If you have that power of -1, you know it's going to alternate. I just do the first 2 by substitution to make sure I get the pattern straight. And right now it's first answer minus second, so the next is going to be plus without substitution. And now I'm just looking at the a sub n part of it. And I'm not really thinking about the power of -1. I'm just going to substitute into the rest of it, the 1 over n factorial part, and make the signs alternate. Okay. So, let's see if it converges. It's definitely alternating, so we'll write that down, which indicates that that's the test we're using. Our a sub n is 1 over n factorial. So first part of the test, what is the limit as n approaches infinity of 1 over n factorial? Well, dividing a constant like 1 by a number that's only getting bigger and bigger means that we're headed toward 0. So we pass that first test. Second test is a sub n plus 1, which would be 1 over n plus 1 factorial. And then I'm going to write over here what a sub n is and hope that it's got the right direction. Now if we're comparing those two fractions, the fraction on the left has a bigger denominator, so that means that fraction is less than or equal to, that worked. That's what we wanted to show, that that is less than or equal to. A sub n plus 1 is less than or equal to a sub n. So that means that, of course, that this series converges. Okay. All right, so now that we know it converges, you might be interested in knowing what this converges to. Oh my goodness, I ran out of room. I hate to split this example over 2 lectures, so I'm going to see if I can squeeze stuff in over here to the right. So I really apologize for doing that. That's not planning to hit very well. So this is the continuation over here. All right, so we're supposed to approximate the sum of that series by its first 6 terms. So we've got the first 4 written. The next one is plus 1 over 5 factorial, and the next one's 1 over 6 factorial. So let me just write those in. What plus 1 over 5 factorial would have been the next one, minus 1 over 6 factorial. And of course the next one, which they didn't ask us for yet, but I'm going to write it down anyway. You'll see why in a second if you don't already know. And it continues. Okay, so we're going to find an approximation for this sum. We're going to add 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial, etc. until we get out to minus 1 over 6 factorial, and then we're going to stop. Okay, so the last thing we add is this negative 1 over 6 factorial. Okay, so if you do that, you'll get 91 over 144, which in decimal form is approximately 0.63194. Okay, so what we know from the alternating series remainder theorem is that the actual sum minus the approximation we just found, when we take its absolute value, that gives us the remaining part of the series, r sub 6. The remaining part after the first 6 things have been pulled off. And according to that theorem, that remainder, that error, is definitely less than or equal to a sub n plus 1. Since n here is 6, that'll be 7. Term. That next term is 1 over 7 factorial, which calculates to be 1 over 5040, which is approximately 0.00002. So that means that the answer we got, 91 over 144, or its decimal form, is no more than 0.0002 off from the correct answer. So what that means is the sum S lies between because that's the distance between the actual answer and the approximation. So we know S lies between our answer, our approximation, minus, so we could go as far as that much below ours, and our answer plus that largest possible error, 0.0002. So in other words, that means that S lies between 0.63174 and 0.63214. So we don't know what the sum is, and many times we cannot find the sum, but you can be very certain what it's close to. It's definitely between those 2 numbers for this problem. So if we were rounding to 3 decimal places, both of those round to 0.632, which means with a lot of confidence we know that that sum is very close to 0.632. And so that's valid. Okay, so that's one type of problem. We're going to stop this and come back into the next video with a reversal of this process where we're trying to find n so that we don't have an error bigger than some given value. So we'll do that in just a minute.